Titan is lying to us. From a distance, it looks like home. It has rivers, lakes, coastlines, rain, clouds, seasons, and a thick atmosphere that wraps around it like a blanket. If you squinted at the right photograph, you could mistake it for Earth. NASA scientists have said exactly that, and that resemblance is the trap. Because Titan isn't Earth. Titan is a freezing, toxic mockery of Earth, a world that borrowed our planet's face and filled it with poison. It orbits Saturn at roughly 1.2 billion kilometers from the Sun, 10 times farther than Earth. At that distance, the Sun is a dim point of light, barely brighter than a full moon on a clear night here. Temperatures at the surface hover around -179 degrees Celsius. That is cold enough to make steel brittle, cold enough to turn methane, a gas you'd smell near a stove burner, into a liquid. And that liquid methane is what fills Titan's lakes and rivers. Not water, methane. When the Cassini spacecraft arrived at the Saturn system in 2004, it carried a passenger, a small probe called Huygens, built by the European Space Agency. On January 14, 2005, Huygens detached from Cassini and fell toward Titan's surface. It took 2.5 hours to descend through the atmosphere, and what it saw on the way down changed how we think about moons, planets, and what it means for a world to look familiar. The atmosphere hit first. Titan's atmosphere is about 1.5 times thicker than Earth's, the only moon in the entire solar system that has a substantial atmosphere at all. It's mostly nitrogen, just like ours, around 95% nitrogen, in fact. On paper, that sounds almost comforting. On Titan, it means nothing. The remaining 5% is a cocktail of methane and hydrogen, laced with trace organic compounds that react with ultraviolet light to produce a permanent orange smog. That smog is so thick that sunlight barely reaches the surface. If you were standing on Titan at noon, the light would be roughly 1,000 times dimmer than a sunny day on Earth, something closer to deep twilight. You would see your hands in front of you. You would not see the sky. Huygens recorded the sound of its descent. Wind. Actual wind, buffeting the probe as it dropped through layers of haze. Titan has weather. It has a hydrological cycle. Methane evaporates from the surface, rises, condenses into clouds, and falls back down as rain. The rain carves channels into the ground, feeds rivers, and those rivers empty into lakes and seas. Ligeia Mare, one of the largest seas near Titan's North Pole, is roughly 50,000 square kilometers, bigger than Lake Superior. Kraken Mare is even larger, somewhere around 400,000 square kilometers, comparable in area to the Caspian Sea. From orbit, radar maps of these features look like coastline surveys of Norway or British Columbia. Inlets, peninsulas, islands, drainage basins. That's the trick. That's what makes Titan so unsettling. The geography is familiar. The processes are familiar. Evaporation, condensation, precipitation, erosion. Every one of those words applies to both Earth and Titan. The machinery is the same. The ingredients are alien. Methane rain on Titan doesn't fall the way rain falls here. The gravity is only about 14% of Earth's, and the atmosphere is dense, so raindrops would be enormous by our standards, perhaps a centimeter across, and they'd fall slowly, drifting down like fat, lazy drops in slow motion. If one landed on your suit, it wouldn't splash. It would spread, oily and cold. Methane is a solvent. It would eat through certain plastics and rubbers. If your suit used the wrong seals, Titan's rain wouldn't just soak you, it would dissolve your equipment. The ground Huygens landed on was another surprise. The probe hit the surface and didn't bounce. It sank slightly, then settled. The data suggested a thin crust over something softer underneath, like wet sand or clay. Except the moisture wasn't water, it was liquid hydrocarbons. The camera on Huygens captured one image from the surface, just one, before the batteries died. It showed a flat plain scattered with rounded pebbles and cobbles. They looked exactly like river rocks on Earth, smooth, eroded, shaped by flowing liquid. The resemblance was so strong that one of the imaging scientists later said it could have been a dry riverbed in Arizona. It wasn't. Those pebbles were made of water ice, hard as granite at those temperatures, shaped by rivers of liquid methane that had long since dried up or shifted course. This is what Titan does. It hands you something recognizable, then reveals what it's actually made of. And the revelation is always worse than ignorance. Consider the dunes. Cassini's radar found vast fields of sand dunes near Titan's equator, stretching for hundreds of kilometers in long, parallel lines. They look almost identical to linear dunes in the Sahara or the Namib Desert. Same scale, same spacing, same sinuous shapes. The sand isn't silicate though, it's organic. The particles are made of tholins, complex hydrocarbon molecules that form when ultraviolet light from the distant sun hits the methane and nitrogen in the upper atmosphere. Those molecules clump together, grow heavy, and slowly snow down onto the surface over millions of years. Titan's deserts are built from chemistry that would be toxic to breathe, toxic to touch, and utterly unlike anything on any beach you've ever visited. There's a detail about those dunes that doesn't get enough attention. They move in the wrong direction. Titan's prevailing winds near the equator blow from east to west, which is consistent with its slow rotation. The dunes, however, point west to east. For years, this made no sense. The leading explanation is that Titan occasionally experiences powerful equatorial storms, brief but violent methane downpours that generate intense surface winds blowing opposite to the prevailing direction. These rare storms are strong enough to overwhelm the everyday breeze and shove the sand the other way. The quiet weather builds the dunes slowly. The storms reshape them in hours. Titan's deserts aren't just alien in composition, they're sculpted by tantrums. And beneath all of it, something even stranger. Cassini measured tiny variations in Titan's gravitational field during repeated flybys between 2006 and 2012. The data told a story that nobody was expecting. Titan's surface doesn't sit on solid rock, it sits on ice. And below that ice, there is almost certainly a global ocean of liquid water, possibly mixed with ammonia, buried under a shell estimated to be 50 to 100 kilometers thick. Titan has two faces. The one on top is a frozen methane world dressed up to look like Earth. The one below is a hidden water world that we can't see, can't touch, and can barely detect. That subsurface ocean raises questions that keep astrobiologists awake at night. If there's liquid water down there, and if the ocean floor is in contact with a rocky core, then there's a possibility of hydrothermal activity. Hot water reacting with rock is one of the most promising recipes for life that we know of. The same recipe powers the ecosystems around hydrothermal vents at the bottom of Earth's oceans. Titan might have the same thing happening right now, 1,000 kilometers beneath those methane lakes, in permanent darkness, under crushing pressure, in an ocean nobody can reach. But the surface has its own strange candidacy. In 2015, a team of researchers at Cornell modeled what a cell membrane might look like if it had to function in liquid methane instead of liquid water. On Earth, our cells use lipid bilayers, thin sheets of fatty molecules that form a barrier in water. That chemistry doesn't work in methane. It's too cold. The molecules don't behave the same way. The Cornell team proposed a theoretical membrane they called an azotosome, built from nitrogen-containing molecules that could, in principle, form stable, flexible structures in liquid methane at Titan's surface temperatures. Nobody has found one. Nobody has proven they exist outside of a computer model. But the fact that the chemistry is even theoretically possible means that Titan isn't just mimicking Earth's landscape. it might be capable of inventing an entirely different kind of biology, one that doesn't need water at all. That thought is either thrilling or terrifying, depending on your tolerance for the alien. There's another piece of evidence that makes the biology question harder to ignore. In 2010, two separate studies using Cassini data pointed to something odd happening in Titan's lower atmosphere. The first, led by Roger Clark at the US Geological Survey, found that hydrogen molecules flowing into the atmosphere from space seemed to be vanishing near the surface. They were going down, but not coming back up. The second study, led by Darrell Strobel at Johns Hopkins University, found a puzzling absence of acetylene near the surface. Models predicted acetylene should be accumulating on Titan. It wasn't. Before Cassini arrived, the astrobiologist Chris McKay had published a paper proposing that if methanogenic life existed on Titan, it would breathe hydrogen and eat acetylene, producing methane as a byproduct. The missing hydrogen and the missing acetylene fit that prediction. Nobody claimed this was proof of life. Non-biological chemistry could explain both observations, but the fact that two independent datasets independently matched a biological prediction made years before the measurements existed. That's the kind of coincidence that makes scientists very uncomfortable and very curious at the same time. What makes it worse is the silence. Titan has all this complexity, all this activity, rain and rivers and seas and weather and hidden oceans, and we have almost no data from the surface. Huygens lasted 72 minutes after landing. One image, a handful of measurements. Everything else we know comes from orbit, from radar and infrared, and gravity measurements made by Cassini during flybys. We mapped Titan the way you'd map a city, by flying over it at night with a flashlight pointed out the window. We saw shapes, we inferred materials, we modeled processes. But we've touched the ground exactly once, in one spot, for barely over an hour. NASA is going back. A mission called Dragonfly, a nuclear-powered quadcopter, is scheduled to launch in 2028 and arrive at Titan in the mid-2030s. It won't land in one place and sit there. It will fly. Titan's thick atmosphere and low gravity make it one of the easiest places in the solar system for powered flight. Dragonfly will hop from site to site across the equatorial dune fields, eventually working its way towards Selk Crater, an impact site where scientists believe liquid water from the subsurface briefly reached the surface and mixed with the organic material on top. That mixing zone is a place where the ingredients for both water-based and methane-based chemistry might have briefly existed together. The engineering alone is a kind of quiet madness. Dragonfly's rotors have to work in an atmosphere 4 times denser than Earth's, which helps generate lift, but at temperatures where lubricants behave differently, where electronics can fail in ways nobody has tested outside a lab, and where the only source of power is a chunk of decaying plutonium-238. The probe will fly for roughly 30 minutes at a time, covering about 8 kilometers per hop, then land, recharge, analyze the soil with an onboard mass spectrometer and gamma-ray spectrometer, and wait for the next flight window. Each hop will take it to a location that was selected based on orbital data from a spacecraft that's been dead since 2017, when Cassini was deliberately crashed into Saturn's atmosphere. Dragonfly is navigating with a map drawn by a ghost. What Dragonfly finds there could redefine what we think life needs. That's not hyperbole. If there are complex organic molecules in that crater that show signs of organization, of something more than random chemistry, it wouldn't mean we found life. It would mean we found a second example of a world where chemistry tried to become biology. And one example is curiosity. 2 is a pattern. Until then, Titan waits. It keeps raining methane into dark rivers that empty into seas no human has ever seen directly. It keeps hiding an ocean of water beneath 100 kilometers of ice. It keeps wearing Earth's face over a body made of poison, cold, and strangeness. Every other terrifying place in the solar system has the decency to look hostile. Venus is a furnace wrapped in acid clouds. Jupiter is a wall of radiation and pressure. They announce what they are. Titan doesn't do that. Titan looks like a place you could land, a place you could walk, a place with shores and skies and weather. It invites you in. And the longer you stay, the more you realize that everything familiar about it is built from something fundamentally wrong. That's what makes it the scariest moon in the solar system. Not the cold, not the methane, not the toxic haze or the hidden ocean or the alien chemistry. It's the resemblance. It's the fact that Titan studied Earth's homework, copied the format perfectly, and filled in every answer with something from a completely different language. We look at Titan and see ourselves reflected back. And the reflection is off, just slightly, in ways that take time to notice and longer to understand. A world that feels familiar but isn't. A mirror that doesn't quite match. If that doesn't unsettle you, spend a minute looking at Huygens' single-surface photograph. River rocks, a flat horizon, haze. It could be anywhere on Earth. It is nowhere on Earth. And in the mid-2030s, a small helicopter is going to fly through that haze and tell us what Titan has been hiding under that borrowed face for 4.5 billion years. I hope you enjoyed the video, and I'll see you next time.